Hi, my name is Mark Zastro. I'm a grad student here at the astronomy department at Boston University. And I'm going to start out by telling a story about an astronomer who probably had the worst run of luck, probably of any astronomer ever. So this starts in the year 1760. Astronomers from Europe are setting out to observe the upcoming transit of Venus from all over the globe as part of an international observing campaign, which you'll hear more about later. One of them is a French astronomer named Guillaume Le Gentil. He's 34 years old, and he says goodbye to his wife and sets sail from Paris for East India. He sails around Africa, past the Cape of Good Hope, to the Isle of France, which is today known as Mauritius. From there, he's supposed to catch another ship to his final destination, the French Indian colony of Pondicherry. But this is where everything starts to go wrong. First, when he gets there in the summer of 1760, he finds out that there are no ships sailing for Pondicherry. There are a couple of reasons. One is that he's gotten there at the wrong time of the year, and the seasonal winds aren't favorable. The second is that France and Britain are at war in India, and the British have laid siege to Pondicherry. It is now a war zone. He waits through the summer and the fall, and no ships want to sail there. He comes down with dysentery. In the meantime, winter passes, 1761 arrives. In February, he finally catches a ride on a French frigate carrying urgent military intelligence for the war effort. They struggle through the weak winds for 5 weeks, but when they finally reach the west coast of India, they get bad news. They're too late, the war is over, and the British have razed Pondicherry to the ground. Le Gentil wants to continue, but the military frigate has no reason to, so instead they return to the Isle of France. And on the way back, the transit happens. The weather is clear, Venus and the Sun are perfectly clear above him, and he actually sets his telescope up on deck and tries to make observations. But he's stuck on a boat in the middle of the Indian Ocean, which means he doesn't have an accurate clock or an accurate position at sea. His observations are completely useless, and he knows it. So now he's terrified for his reputation. He's paranoid that his fellow astronomers will accuse him of cowardice. In his memoirs, he literally begs his colleagues to read his daily diary for proof that he wasn't slacking off, and that these bizarre circumstances were completely out of his control. Now, here's the amazing thing about this guy. Maybe it's from desperation, maybe it's from a sense of duty to science and knowledge, I don't know. But after having spent over a year trying to get to East India and sailing thousands of miles, he decides to stay around and wait for the next transit in 8 years. It's the last one that his generation could see, so he might as well stick around the Indian Ocean. He spends most of his time on the Isle of France and the surrounding islands. He studies the geography, natural history, the indigenous cultures of the region. And so 6 years later, he sets sail to try again. This time his calculations tell him that the best place to view the transit is Manila in the Philippines. But there's a problem. That's a Spanish colony, potentially hostile to the French. And indeed, when he gets there, the governor is a tyrant who, he writes, is a restless man of evil intentions to the French in general. Now, he had prepared for this scenario. He actually wrote to the court of Spain for letters of recommendation, saying that he was a scientist and that he had the blessing to observe the transit for Manila. He had them sent on the fastest ships available. But when he presented them to the governor, they had arrived so fast that the governor was convinced they were forgeries. So in the end, Le Gentil had to pack up, left Manila, and sailed to where he'd meant to go originally, to Pondicherry, which by now had been transferred back to the French in ruins. He set up his observatory in the ruins of a palace just to the right of the flagpole in this illustration, and he waited. And for the entire month leading up to the transit, the mornings were perfectly clear. But when he wakes up on the morning of the transit, it's completely filled with clouds. He writes, "From that moment on, I felt doomed. I threw myself on the bed without being able to close my eyes. He waits for the weather to get better, but instead, a freak squall blows in. When the moment of the transit arrives, he is completely clouded out." Of course, after the transit, the rest of the day is perfectly clear. Le Gentil was heartbroken. He fell into a severe depression. For 2 weeks, he's so depressed that he can't even bring himself to write in his journal what happened. He comes down with dysentery again, And by the way, the weather in Manila that day was perfectly clear. Now, he just wants to get home, but that's not so easy either. His first ship leaves him behind in the Isle of France because he's so sick. His second ship runs into a hurricane and snaps his mast, and his third ship runs through a horrendous storm at the Cape of Good Hope. But he survives, and when he finally gets back to Paris, 11 years has passed. And after all of his misfortune, the worst is still to come. His wife had left him and remarried. She thought he was dead. The manager of his estate wound up being incompetent and lost a huge chunk of his assets. And his heirs were circling what was left, ready to split them up and claim them. And maybe the most ironic of all, he lost his seat in the French Academy of Sciences, the organization that sent him in the first place. Short of giving one's life, it's hard to imagine paying a higher price for scientific data. So, after reading and finding out about this, I guess the question that runs through my mind is, why did he do it? Why wait 8 years in the Indian Ocean instead of going home to his family? Was it worth it? Why was the transit of Venus so important, and what would that knowledge do for humankind? So tonight, we have 3 more presentations, all about the transits of Venus and what they're worth. The first one is transits, why they're so rare, and what was so important about them in Lejean's time. The second is on the scale of the solar system, how that transit data from other astronomers like Lejean taught us just how small we were and just how big our solar system was. And the third, what are transits good for today? How transits of extrasolar planets, alien planets around other stars, may answer one of the most basic questions we have ever known. Are we alone?
Hello, my name is Carol Carva, and I'm presenting on Venus and its transits. Basics of our solar system, at least the inner planets, are displayed right now. We have the Sun in the center, with Mercury going around in orbit and Venus going around the second planet from the Sun, and of course Earth is the third planet. Venus and Mercury are both going much faster around the Sun, such that once every year and 7 months, Venus laps the Earth. And when Venus is actively passing the Earth, we call that an inferior conjunction. So you would say, well, why does Venus pass between the Earth and the Sun once every year and 7 months? Why am I hearing it doesn't happen more than once a century, or more than once or twice a century or so? And the reason for that is that the orbits of Venus and Earth are tilted with respect to each other. So Venus is going around in this plane, and Earth is going around in this plane, so it actually takes a very particular set of circumstances. And when Venus is below the orbital plane, it actually ends up looking like Venus is passing by the Sun as neighbors. But when we have the point where the orbital planes intersect, we have either Venus looking to go southward diagonally across the Sun or northward diagonally across the Sun, which depends on when you're having it happen. In 2004 and this transit, it'll look like it's going southward. And people have been seeing transits of Venus since the ancient times, which is why in the geocentric models, Venus appeared between Earth and the Sun when Earth was at the center. The problem was that the geocentric model was so bad that you weren't able to predict when transits would happen. That's because Earth is not actually the center of the solar system, which Copernicus proposed, and then Kepler refined the actual models using a lot of observations. And he refined them so well that he was able to predict that in 1631 there would be a transit. He died by that time, but there was a man called Gassendi who was watching from Paris. Regrettably, Paris was not able to see the transit. But in 1639, 8 years later, Crabtree and Horrocks were able to see the transit. And that is awesome. It means that we're able to predict the transits now. We've got a much better model of the solar system. Problem is that the model didn't take into account actual scale size, so they weren't sure how far away it was exactly. And Rachel will be talking a little bit more about that later, but in the late 1600s, there was a proposal for how to use the transit of Venus to find what the actual scale was. And so in 1761 and 1769, the next 2 transits that happened, people had a number of international collaborations and sailed all over the Earth in order to figure out how far that was. And they came up with an estimate of about 96 million miles. Along with that, they think they discovered the Venusian atmosphere, because as Venus was entering, and we may see this ourselves, you saw a halo around Venus, and a Russian astronomer decided that was the atmosphere. They also thought this thing called the black drop effect was due to Venus's atmosphere. What that is if you take, it's actually a result of, is if you look at your fingers really closely together, they're not actually touching, it looks like they're touching. And that's sort of what caused this black drop effect, which also gave them slightly inaccurate results, which is why they came up with 96 million miles instead of 93 million. So in 1882, since they were not satisfied, they actually took photographs, and from those photographs got more accurate timings, and from that got a more accurate value of the distance between the Earth and the Sun of about 93 million miles. And after that happened, they were really wowed and excited about the future. And what the state of science will be when the next transit season arrives, God only knows. Well, by that point, in 2004, which was the next transit, we'd had a number of observations and nailed down the value better using other methods. But we also learned a lot more about Venus using bigger telescopes, the space age, and we know that it's a very hot planet. We know that it's very similar in many aspects to Earth, except for the atmospheric effects and the lack of magnetic field. But it's really neat to have such a close neighbor to the Earth that is so much like the Earth in so many ways and so different in others. We're still learning from Venus today, in that we can look at Venus and compare where it is in the solar system to where we may find habitable exoplanets, or where they may not be habitable because they're too close to the Sun, which Mesh will be talking about later. And it points us towards what we can do to look at how we can look at the exoplanets to see what's going on with them. Thank you.
Great. Hi, my name is Rachel Paterno-Muller. I will be discussing the scale of the solar system with you today. So, this is a overhead view of what our solar system looked like a few weeks ago. It's not an actual picture, but it's a model. And as you can see, the solar system is mostly empty space. The planets are very small compared to the distances between them. So you can see Neptune, Uranus, Saturn, Jupiter, and then a lot of empty space between them. And you can't see the inner planets on this image, but if you zoom in, you can get a good look at how their orbits are. We've got Mercury, Venus, Earth, and Mars. The inner solar system is a little bit more cramped as compared to the outer solar system. So by the mid-17th century, when Kepler was around, people knew the scale of the solar system. They had what they called an astronomical unit, and that was the distance between the Sun and the Earth. And then they knew how the other planets scaled compared to that, so they knew that Venus was 7/10 of an astronomical unit, but they didn't know what an astronomical unit was in actual meters or miles or units of measurement that they use on a day-to-day basis. So they wanted to come up with a way to get that value, and there were a couple of ideas tossed around. They were a little bit difficult. And then Halley, of the comet, proposed using transits to determine what this actual numerical value was. And you can use Mercury or you can use Venus. Venus is a better choice because it's closer to Earth, and thus the parallax angle is larger and easier to measure. So a quick digression into what exactly parallax is. You may be familiar with it. If you hold your finger out in front of your nose and then close one eye and close the other eye, your finger appears to jump. And parallax is just that. It's the apparent motion of a nearby object with respect to a distant static background. So people are going to use the parallax of Venus during its transit to determine the distance. So you can see, if you're at point A on the Earth and you look at Venus, it appears to be traveling across this part of the sun. This is a highly exaggerated figure. And if you're at point B, then you would appear to see it up here. Again, the distances were not this extreme. This is very exaggerated. And you know the distance between point A and point B because they knew what the radius of the Earth was. You can measure this angle here. That's the parallax angle. That's what good measurements of the transit will tell you. And then you can use trigonometry to determine the distance to Venus from Earth, and then using what you know about the scale of the solar system, determine what these actual distances are. So they were able to use the transit of Venus to do that and get fairly decent estimates, as Carol mentioned. And so that tells you a little bit, that tells you about the distances of the planets. But what about the sizes of the planets as compared to each other? So these are the inner solar system planets, again, Mercury, Venus, Earth, Mars, and then the Moon thrown out there for good measure. You can see Earth and Venus are similar in size. Sometimes they're called sister planets, even though, as Carol mentioned, they are very different. Mars is fairly small, as is Mercury. And these comprise our inner solar system, the rocky planets. Now, we live on Earth. It seems like a big place, but when compared to the gas giants of the outer solar system, you can see just how small these inner planets are. Here are the inner planets. Here's Jupiter's great red spot. All the inner planets look like they would fit inside the great red spot of Jupiter. And then you've got Saturn, Uranus, Neptune, all very large when compared to our rocky inner planets. But what about if you compare these seemingly large objects to the size of the sun? Well, when you do that, Jupiter seems very negligible in size. Here's Earth out here, doesn't even begin to compare to the size of the sun. So all the planets in our solar system are actually quite small compared to the star they orbit. And even the larger gas giants are actually fairly small when compared to our sun. For a while, our solar system was the only star system we knew about. Up until very recently, we had no idea that there were other planets around other stars. But with the advent of good telescopes, we were able to find new planets orbiting other stars. And for more on that, Maj will be following up. Thank you.
Good evening, my name is Majmata, and tonight I'm going to talk to you about exoplanets and transits, such as the event that you're watching tonight with Venus, are still applicable today. And so the next few minutes, I'm going to convey to you what exoplanets are, why we care about them, and how we can find them. An exoplanet is simply a planet that orbits a star that's not our sun. It can also be called extrasolar planet. And you may have heard some buzzwords in the media, such as hot Jupiter or super Earth. A hot Jupiter is simply a Jupiter-like planet in that it's a gas giant, and which has the same size as Jupiter, more or less, that orbits closer to its star than Jupiter does to our sun, making it hotter. Similarly, a super Earth is an Earth-like planet that is rocky, that's a little bit bigger than the Earth. The reason we're so fascinated with exoplanets is that they can help us answer some age-old questions. Is there life anywhere out there? Can the human race survive on another planet? Or are we alone? And so the hunt for extraterrestrial life, yes, I do mean aliens, and other habitable planets, is what drives the search for exoplanets. And once one is found, the next step is usually to figure out if it's in the habitable zone. The habitable zone is a region around each star where water can be found in its liquid form. And for our solar system, the habitable zone extends from just beyond the orbit of Venus up until about twice the orbit of Mars. The habitable zone is different for different types of stars. And it's not enough for a planet to be inside the habitable zone to be considered a habitable planet. It also has to be the right size. If a planet is too small, which is the case for Mars, for example, then it won't have enough gravitation to sustain an atmosphere. So most of the atmosphere would disappear, it would just escape, which is another condition that would not allow for that planet to be habitable. So a habitable planet is considered one that is inside its star's habitable zone and one that is the right size, which is typically about the size of the Earth or a little bit bigger than that. There are lots of ways that we can find exoplanets. I'm just going to highlight the three most popular ones. The first is called direct imaging. If you train your telescope to a star and look at that for a while, then chances are you're not going to see anything other than that star. But if you put a little mask on your telescope, just enough to cover that star, if you're lucky, you might see some spots around it that are planets. If the planet is too close to its star's glare, or if it's too small, then you won't be able to see it using this method. And so direct imaging really favors planets that are farther away from their star or that are large. Another method is called the Doppler shift. The mechanics of a planet orbiting around its star make its star wobble by just a little bit. A telescope looking at that star can see that wobble. We can get information about the mass of the planet, even though we can't see it. The bigger the planet, the larger the wobble, the more likely we are to see it. And so this method also favors larger planets. The transit method is also really popular in detecting exoplanets. When a planet is passing in front of its star, just like Venus is doing tonight, it blocks some of the light coming from that star. And a really sensitive camera looking at that star can detect this drop in brightness for all sizes of planets, and not just the big ones. We can use this measurement to figure out how big the planet is, how far away from the star it orbits, and also how hot it is. And so once an exoplanet is detected, there are usually different instruments that are used to look at it to get as much information as possible from that planet. I'm going to talk about one such tool that we use, and it's called Kepler. As Carol mentioned earlier, there was this cool astronomer called Johann Kepler. He was a German astronomer who lived in the late 16th and 17th and early 17th centuries, and he laid the laws of planetary motion. He also published the Rudolphine tables in which he predicts the transits of Mercury and Venus. So it was very fitting for NASA to name a mission after him. The Kepler Telescope looks like this. It lives in space, and it was launched 3 years ago, and it's still there today. Its sole purpose is to find exoplanets using the transit method. Kepler stares at a patch of the sky in the Milky Way that is extends up to 3,000 light years away and stares at about 150,000 candidate stars. You can stare at an area of about 10 by 10 degrees, which is about the size of 2 open hands. And it looks between the constellations of Cygnus and Lyra, which you can see on a clear summer night. Kepler is so sensitive, it can detect a drop in brightness of 1 part in 10,000. That's like a flea passing in front of a car's headlight. I'll just wrap up with some statistics of where we are currently. As of about 3 months ago, there have been over 2,000 exoplanets detected, about a third of them using the transit method. About 250 of those planets are Earth-sized, and 50 of those are in their habitable zone. If we extrapolate the statistics out to the entire Milky Way galaxy, we get about 2 billion potentially habitable worlds. Not only have we been able to discover so many amazing exoplanets, we've also been able to discover amazing systems that we never knew existed before. One good example is Kepler 16b. That's a Saturn-sized gas giant that orbits around 2 stars. Now, this used to be the stuff of science fiction in the past, but it's not unlikely that in the near future, we might find a genuine lookalike for Luke Skywalker's home planet. So with that, I thank you and open the floor to questions.